Nice. Hello, everyone. First of all, thanks Zeta Alpha family for having me here. It's super exciting. I hope all of you are having a good time. So today I'm going to talk about transfer learning and more particularly how to use transformer more efficiently, how to adapt these large models more efficiently by using adapters and hypernetworks. I'm sure all of you know this standard paradigm for transfer learning in NLP for this example, but I just want to start with very briefly. So normally, when we have a really large language model, this large language model is pre-trained with a huge amount of monolingual data, right? Even if it is multilingual model, it's a monolingual training, basically. And it's trained with some sort of language modeling objective, maybe mask language modeling objective. But when we have a target task, we need to adapt this large language model, right? This is the main paradigm today. Maybe these days it's slightly changing with this prompting or in context learning, but I think still the dominant paradigm for transfer learning is this fine-tuning. And for the fine-tuning, we have relatively small amount of task-specific data, and we probably add some downstream task head, and then we want to fine-tune, we want to adapt the model. So let's have a little bit closer look. So this is one single transformer layer. It has multi-headed attention block and self-attention block. And when we fine-tune it, we fine-tune the full model, right? So it means we fine-tune all parameters of the model. So this works pretty well, most of the time state-of-the-art. And if you have enough data, probably super easy with the current libraries and all. But if you think this language model is getting bigger and bigger, we have a very big problem, right? This is a very inefficient way to adapt a large language model. Because even the BERT has hundreds of millions of parameters, now going to T5 and GPT-3, trillions of parameters, and yeah, we cannot fine-tune all the time. But also there is another problem, which we call it catastrophic forgetting. This standard fine-tuning is really prone to this catastrophic forgetting. What does it mean? This catastrophic forgetting means we fine-tune a model, then it tends to forget the previous knowledge. Let's assume that we have 10 different tasks, 10 different downstream tasks. We cannot fine-tune task 1 and then fine-tune task 2, and we cannot use for the task 1, because when we fine-tune for the task 2, it probably will forget in a degree task 1. So in practice, what we end up, we need to have 10 different versions of base model, and we need to fine-tune 10 times of the base model, right? It's, again, inefficient. So what would be the alternative? One alternative is a really good alternative is adapters. Maybe I can start with asking how many of you heard of adapters or used? Yeah, pretty popular, very nice. So adapters basically a parameter efficient version of fine-tuning. So how we use it? We want to add a very small module within a transformer layer. It could be a different position, but most of the time these days we use only almost the end part of a single layer, and we put very small feed-forward network. So it needs to have a down projection and up projection, because we need to keep the same dimensionality, because we are adding inside the transformer layer, right? And more importantly, when we fine-tune with adapters, we do not touch the main network parameters, but we only fine-tune adapter parameters, which we initialize randomly in the beginning. So if we think about the number of parameters, then our adapter parameters are probably so much smaller than the full model parameters. So by the way, this adapter parameters depends on your down projection. If you project a very small dimension, you will probably have very, very small set of parameters that you will fine-tune. And it is super efficient. But efficiency is something, but of course we want to keep the same performance, right? So let's see it really works. So this is, I think, the first paper that use adapters in NLP domain from Google Brain, I guess. So they used 9 different glue tasks. So in the first line, you see BERT large model. So you need to fine-tune all of the parameters. So all the parameters fine-tuned. And for 9 tasks to reach the state of the art, you need to do this 9 times. But for the adapters, you only fine-tune 2 to 4% of the parameters. So your new parameters in total for 9 tasks is really small, 1.2, from 1 to 1.2. And if you look at the total overall performance, it's almost same, state of the art again, right? And also if you look at the plot, this shows the delta difference between full fine-tuning and adapter tuning. Even very small number of parameters, your performance is quite robust and very similar to full fine-tuning. It's really efficient and it's really perform well compared to the full fine-tuning. But efficiency not only benefits comes with the adapters. So we said this catastrophic forgetting is a problem, right? So to mitigate this catastrophic forgetting, we need some sort of modules that will encapsulate the information to not forget later on, right? We don't want to forget the pre-trained knowledge, so we don't want to update the pre-trained parameters, but also we don't want to forget the task knowledge that we just learned. Actually, adapters also gives you this capability because this is more like a plug and play system, right? We plug the small module, train it for a task, then we can take it out, and we can plug another module. So this is kind of really a good way to keep information. So because basically adapters actually transforming the pre-trained knowledge for a downstream knowledge. And it is quite modular, right? And this modularity is super important because it may open up different doors, different directions. Maybe you just want to fine-tune your model for name entity recognition. You can just fine-tune it for English NER. But maybe you want to adapt your pre-trained model for a domain or for a new task. Then you can do MLM training. It's more like a domain adaptive fine-tuning. And you can then keep some sort of language-specific information within adapters. And you can also do this for any language. And there is really a cool paper from Jonas Pfeiffer. It's called MEDEX. When you have different sort of adapters, you can combine them. Maybe you can fuse them for the new task, or you can replace them for a cross-lingual transfer learning. So it's really, I won't go into details of that, but adapters give you a very nice framework to play with because it's super modular. But it's not everything is perfect, of course, right? There are some limitations. So first limitation is, yes, these are modular architectures, very small, but there is no sharing between one adapter to another one. Let's say you have different tasks, but some tasks are very similar, but you cannot share any information between those tasks because by definition you train one adapter per task. Or you have some languages, maybe 3 of your languages from the same family, you want to share some sort of information for those 3 languages. With the current adapter architecture, unfortunately you cannot do that, right? So sharing only happens in the pre-trained model. But also, so adapters are quite parameter efficient, but if you have like hundreds of languages, your parameters will be multiplied by, number of parameters will be multiplied by number of languages or number of tasks. So parameter number will increase linearly with your number of tasks or number of languages. So there's a kind of scaling problem, right? So one of the alternatives is Hypernetworks. So how many of you heard of Hypernetworks or maybe used? Yeah, very nice. So Hypernetwork is some sort of conditioning mechanism. So you can think like we have a main network. This probably will be some pre-trained model, but there are some limitations. I will come to that point later. And we have an external, relatively smaller model, smaller network. And our actual input goes through the main network, but we have some sort of auxiliary input that we want to condition our model on, this auxiliary input. Then our hypernetwork actually generates the parameter for the main network. So actually, we are not training the main network, but we are training the hypernetwork. And in the runtime, hypernetwork generates the parameters for the main network. So why this is really nice model? Because if we have different sort of auxiliary inputs that we want to condition our main model, but we also want to share information, then we just need to train one hypernetwork for all the possibilities. So sharing is some kind of maximum here. So I'm not sure there is such a model. I just want to give a very simple example. Let's say we have a generation model. Normally we give prompt and we have some generated text. and we want to condition our generation to the style. So one way, possibly, would be using the hypernetwork, because our style is an external conditioning, right? We can give style embedding to the hypernetwork, and hypernetwork can generate parameters for the main model, which generate the text condition to the style. So this is more or less the idea. So we have a desired objective, but we also have an auxiliary input that we want to condition on. So before the adapters, I'm not sure in the vision domain, but in NLP domain, using hypernetwork for the pre-trained models was not really possible, because let's think a bird model. It has already hundreds of millions parameters. If you want to multiply all these parameters with another model, which will be multiplied by a hypernetwork dimension, then the parameter size is so high. So we cannot generate all bird parameters with another model, right? This is not practical, basically. But if you already have something like various adapters, very small modules, then we can generate the parameters of adapters by using a hypernetwork. Actually, these two concepts is super fitting to each other. This is one example. For example, we have multilingual learning setup. We don't want to train one adapter per language, but we want to train a model for multiple languages at the same time. But we also want to benefit from adapters, because adapters have some sort of modular approach. Also, adapters create this encapsulation, right? Then we can use a hypernetwork, giving a language embedding as a conditional input. Then our hypernetwork can generate the parameters for adapters. So I will come to the generation part later, but what is this hypernetwork actually, if you ask this? Could be any kind of linear transformation or nonlinear transformation. So you can use a very big model as a hypernetwork, but you can also use just a dot product operation as a hypernetwork. So it depends on how complex your task is, right? That's the idea. So I put here very small feed-forward network, basically a multilayer perceptron in this case. So what are we gaining with hypernetworks plus adapters? First of all, as I said, maximum sharing. We cannot share with the adapters, but with the hypernetwork, we can share. By using, well, we have sharing advantage, but also we have modularity advantage, right? So if we use for, multilingual setup, in the runtime, we are creating a language-specific capacity, but we are training only one hypernetwork. Also for efficiency. So adapters are efficient, but our parameters are linearly increased with number of tasks or number of languages, right? But for the hypernetwork, our parameters are increasing only with the hypernetwork size. Let's say if we keep hypernetwork size fixed, then even if we increase the number of languages, then our parameter size will be same. So in that respect, it is more efficient and more scalable, I think. So of course, these are very nice things, but does it really work? That's the main question, right? So we tried it, and it really works. So first, I want to show you a multilingual learning example. Okay, I will be very quick. So this is basically a multilingual dependency parsing model. So we use hypernetwork. It even works better than monolingual state of the art. So it's quite impressive, right? Also, there is multitask setup, because we can just change this language embedding with the task embedding. Then it will be multitasking. This hyperformer from Mahabadi et al., very, very nice paper, by the way, also works better than adapter baseline and full fine-tuning baseline. So we have less parameter, faster training, and better performance. Very nice. And this is the last. Can we merge different sorts of information with the hypernetwork? I think this is quite ambitious, but very important point. Actually, this is very recent that we tried. So we merged task information, language information within a hypernetwork. So it takes a concatenation of this task and language embeddings and generate some sort of composite adapters. These adapters are now not for only one language or not for only one task, but any combination. So what is the gain with that? Let's say we have Arabic name entity recognition data, but Turkish part of speech tagging data. So we have two missing, right? Turkish NER and Arabic POS. But if we use some sort of this kind of architecture, then model already can fill the unseen combination, because we are learning language representation separate and task representation separate. In the runtime, model can learn to combine these two representations for unseen combinations. This is really important point for zero-shot transfer. Also, we can add MLMing like a MEDIX. We can add another language with MLM. Also, just to increase the efficiency a little bit more, we can add a layer ID. And for each layer, we can just use only one hypernetwork for the full model. So there are lots of numbers. And I think the short story, it performs very well, almost as good as state of the art, but trains so much faster, computationally more efficient, and it works in the mixed language and task setup, which the other model cannot work in that case. Yes, the takeaways. Adapters are really good alternative for fine-tuning, quite parameter efficient, train faster, and works as well as full model. You can encapsulate information, and then you can use it for different combinations. You can stack them, fuse them. And if you have multitask or multilingual setup, then you can use adapters with hypernetworks, which works even better. Also, you can use everything at the same time. Yes, that's all. Hyper thanks to all of you.
All right, do you have any questions from the audience?
Hi, thanks for the interesting talk. My question is those auxiliary inputs. How are they generated? Is that kind of done jointly with the training of the hyper network?
Yeah, that's a really good question actually. So commonly, oops. Let's keep it simple. Commonly, we know it could be embedding, and if it is embedding, you can train with end-to-end fashion together with the hypernetwork itself. But if your auxiliary input is a text, then you can use something that can take input as text. So there is no really a limitation there. Whatever you need, you can put as auxiliary input. But in my experiment, for example, I use embeddings as a language. So for the language, I use embeddings.
We have another question at the back. Maybe you can get up, because I don't think the mic scale is long enough.
Thank you for the great presentation. I was wondering if, since you said you're using the language embeddings for the context, right? Can this basically zero shot to any other task that you get embeddings from a text model?
For this particular example, this doesn't work with the zero shot, because you need to learn language embedding at the same time. If you have a language that you don't have training data, you cannot learn language embedding. But if you have something that you can give a language embedding as black box, then you can use for zero shot.
Yeah, like can you parameterize on the output of, like, you run GPT-3 on the name of your task and then you give that as
yeah, you can do, or even simplest, you have, let's say, typological features. You can project typological features to language embedding. Then when you have a new language, you can just generate a language embedding and use it with hypernetwork.
Thank you.
All right, do you have any other last question?
Thank you for the talk. I wanted to ask you about catastrophe forgetting. What prevents the hypernetwork from collapsing to the latest training language?
Because still we are training the adapters. So this, yeah, you're right, because in the hypernetwork case, there is a danger of catastrophic forgetting because we are training one model, but we are training very small number of parameters, and still it is generating separate adapters, which has a better optimization trajectory, let's say.